Hello, everyone, and welcome to Office Hours with the Meter Group team. Today's session will focus on canopy measurements and how to get them right. And we're shooting for about 30 minutes of Q&A with our experts, Jeff Ritter and Chris Chambers, whom I will introduce in just a moment. But before we start, one housekeeping item. If you're watching this video and you think of a question you'd like to ask our science experts, we encourage you to submit your question on our website at metergroup.com. And then someone from our science and support team will get back to you with an answer via email. All right, with that out of the way, let's get started. Today, our panelists are application specialists Jeff Ritter and Chris Chambers. Jeff Ritter is the product manager for plant canopy and atmospheric monitoring instrumentation here at Meter. He earned his master's degree in plant physiology from Washington State University, where his research focused on leaf-level gas exchange and the impact of plant biochemistry on the measurement of the global carbon cycle. Prior to working at Meter, he held a research faculty position at Washington State University in the Department of Crop and Soil Sciences. Chris Chambers operates as the Environment Support Manager and the Soil Moisture Sensor Product Manager at Meter. He specializes in ecology and plant physiology and has over 15 years of experience helping researchers measure the plant. He specializes in ecology and plant physiology and has over 15 years of experience helping researchers measure the soil-plant atmosphere continuum. Thanks for joining us today, guys.
Thanks, Brad.
Thanks, Brad.
Hi, Jeff. How you doing?
Doing well. How are you, Chris?
Pretty good. Ready to talk about some canopy science?
Always, yeah. I'm always excited to dive into plant physiology and canopy science. So, where do you want to start?
Well, it looks like we've got some questions about stomatal conductance.
Great.
So, first off, I suppose we should define it for the new folks out there that are just diving into the measurement.
Define stomatal conductance. Okay. So I think, first we kind of need to define what stomata are,
right,
and what they do, what the functions of those are.
Start with the anatomy. Okay.
Yeah.
And so a stoma is a leaf pore that allows gas exchange within the leaf, right?
Right. So sometimes people talk about it like it's analogous to the pores of your skin, which in some ways it is, but it is important to remember that it's actually kind of more like your mouth, and that a plant has a lot of dynamic control over its stomata, where it can open and close it in response to the environment. And it does that to regulate basically what it's trying to take in and what's leaving. So right. CO2 is coming in and water's leaving, and a plant can control its stomata, how open they are, to control those two variables.
And the critical function here, why everyone is interested in it, why you would want to measure stomatal conductance, is because it's the plant's minute-to-minute control over how much water it's losing.
Yeah, there's a big trade-off between a plant has to have its stomata open to take CO2 in, and it needs CO2 for a lot of its physiologic functions to store energy. And when those stomata are open, it's losing water. Yep. So the plant needs to tightly control that. So you can tell a lot about a plant and essentially how happy that plant is if you know something about its stomatal conductance.
And that's why we like to measure it. And just to hammer home how critical it is, plants might need to close their stomata to not just to conserve water, but even to prevent death. If there's not enough water in the soil, the stress on the plant pulling water out of the soil becomes greater and greater. And if that water column breaks, then the plant may not be able to move any more water. And that's a really dire situation for it.
Okay, so if you say you are able to measure the stomatal conductance of a plant, what does that tell you?
The important thing to keep in mind when you are looking at stomatal conductance data are the variables that affect it, right? And those are light, right? If there's no light, like at night, stomata are typically closed. There's no photosynthesis to be done. So some plants, depending on what type of photosynthetic structure they have, they just close their stomata when there's no light or at different light intensities. Water loss, right? Typically, if you have a high VPD, vapor pressure deficit, then the stomata are going to be closed to conserve water. Anything else? What am I forgetting?
I think that's it in a nutshell. And I think the real answer to that is that there's so much that can affect stomatal conductance that you need more context than just a stomatal conductance number. As you mentioned, there's even different types of photosynthesis that certain plants can do that's really going to impact that. So if you're trying to measure stomatal conductance in a plant that uses crassulacean acid metabolism,
like a cactus,
you need to know that before you measure it. Otherwise, your numbers aren't going to make any sense.
Right.
So if you're measuring stomatal conductance on an almond tree and then you try and compare it to a nearby grass species,
like
you need
maize.
you need the context of what a baseline is for those to really be able to interpret what that number means.
Right. And so here's a question that comes up quite often. How does stomatal conductance relate to water loss? And that's a question that isn't necessarily intuitive unless you look at the math. And we can look at stomatal conductance as kind of how much water the plant can lose, right? So we typically express water loss as ET, and it's going to equal the stomatal conductance times the vapor pressure deficit, right? Yeah. And just to break this down, this VPD is basically the tension on the water coming out of the plant, right? So what the gradient is to drive water loss. And this is kind of, the stomatal conductance is basically the size of the pipe, right? So the difference in your gradient times the size of your pipe is going to equal the total water loss.
So ultimately then, the stomatal conductance is the size of the pipe at which water can be lost. Mm-hmm. But you're saying a measure of stomatal conductance is not the same as measuring how much water the plant is losing.
Exactly.
Okay.
Exactly. And the way the plant controls how much water it's losing, how it controls its stomatal conductance, how much water it can lose, is that you've got the density of stomata on a leaf surface, but also their state of closure.
Right. Okay. And, every species, every variety, even looking at the stomatal density in one variety grown in different environments, it's going to be different. Mm-hmm. Development plays a big role in stomatal density. So you just need to be careful taking all that into account when you are measuring.
Especially species, because
yes.
Every species has its own water management strategy, mm-hmm. and stomatal conductance play a big role in that, in the regulation of those stomata.
Okay. So maybe let's get into some of the measurements that are needed. I think, so you've outlined the general form of the equation that we need here with the simplified version of Fick's law, but what do we need to actually measure stomatal conductance? Ultimately, whatever you're doing, you have to make a measurement of a couple of the parameters outlined in this equation. Mm-hmm. So whether that is measuring the total flux and then having some way at getting it the individual concentration of both inside of the leaf and outside the leaf, that can get you at conductance. You essentially need to be able to measure a couple of the parameters outlined in the simplified version of Fick's law. So that's, there's devices out there that will do it with a capacitance type RH sensor.
Mm-hmm. Like the SC1.
Like the Meter Group makes an instrument called the SC1. There's open path systems that will use infrared laser that measures water concentration. And so there's a lot of ways, or there's multiple ways to do it. It just depends on what works for your question, what you're looking at. Right. I kind of want to talk also about, because we're talking about what parameters impact your measurement of stomatal conductance. Mm-hmm. What's the ideal situation that you should be measuring stomatal conductance in?
Anytime that you want to know your plant water status, like from minute to minute or at a given time of day. Now, we've already measured some things that affect stomatal conductance, right? Like light, like how much water the plant is losing.
There's so much that goes into it that attempting to be consistent, if you're trying to compare one plant to the next, is going to be crucial. So
that's right.
And you can't say there's one ideal time to measure stomatal conductance necessarily, because it really comes down to what you're asking. Obviously, if you're interested in pre-dawn measurements, that's going to force your hand there. But otherwise, if you go out on a cloudy day and it's even the same time of day as it was yesterday, that cloud coverage is going to impact stomatal conductance. So it's about attempting to establish a baseline and then seeing how plants respond in different environmental conditions.
That's right. And even within a plant canopy, a leaf that's shaded all day or is at the bottom of the canopy and is always shaded, it's going to have very different stomatal conductance numbers than something that gets full sunlight. And you could see this in plant morphology too, in leaf morphology. The leaves at the top of a tree are generally smaller and have less mass than leaves at the bottom of the tree. And so your stomatal conductance will follow those similar patterns, where if it's cooler at the bottom of the tree and you get less light, you'll probably have a little bit lower stomatal conductance, or it could be higher stomatal conductance because it's losing less water. There's just a lot of variables to balance there.
So then let's say we go out and we measure stomatal conductance, and this is one where we've been making these measurements for a while. How do we interpret those? Like what does that mean as far as stress is concerned? I'm interested in measuring plant stress.
Right. Well, it really depends on the species, right?
Yeah.
I think I've seen some, we have an application note about using the SC1 in vineyards, and that has some specific numbers in there that kind of give you a guideline of how happy the plant is in any given stomatal conductance range. But generally, 0 to 50, the stomata are going to be pretty closed, right? The plant's conserving water. It may not necessarily be stressed. It may have its stomatal closed so that it avoids stress. But it's not very active right now. It's not doing photosynthesis, and it's just trying to protect itself from water loss.
Yeah, I think that's a good way to look at it. Is those numbers will tell you how actively that plant could be losing water, not necessarily whether the plant is stressed from that. That's up to your analysis from what you know about what condition that plant is in. Stomatal conductance?
Just anytime you want to know leaf level water loss.
Yeah, I mean, stomatal conductance is extremely important anytime you are interested in looking at physiological properties of the plant. We actually, even when you're measuring something like photosynthesis and trying to look at what the plant is capable of yielding, that stems from understanding stomatal conductance to water vapor. And from there, you can get it to CO2 and use that in calculating photosynthetic uptake. So it's important for water loss. We haven't talked about it too much, but stomatal conductance is also important for temperature regulation for a plant. Right. So if you are interested in heat stress, it's important in those studies. You can use heat of the canopy and relate that to stomatal conductance and how that's stressed. So stomatal conductance is one of the major ways that a plant controls how it's responding to its environment.
But that also is a great proxy for plant water status, is just measuring the canopy temperature with an infrared thermometer or something like that. So if you want something more canopy level rather than leaf level, then an infrared thermometer, and then you're looking at the difference between the canopy temperature and the air temperature, right?
Yeah.
And you can kind of get a proxy for not necessarily stomatal conductance, but general water loss of the plant canopy.
Right.
How can the SC1 be used to measure leaf transpiration? We touched on that a little bit.
Yeah. So anytime you have stomatal conductance and you want to get to transpiration, keep in mind that if we're talking about transpiration, we're talking about the flux parameter in if we're going back to the Fick's law of diffusion. So with stomatal conductance, we have one measure of conductance, but there are others in that system that you need to account for to get the total conductance. So even if you have concentration of water inside the leaf and outside the leaf, and you have stomatal conductance, you still have to take into account a couple of other points of resistance, namely the boundary layer of your leaf itself.
Right.
So you've got to take into account once that water vapor is able to be conducted through or diffuse through the stomata, what then happens at the boundary layer of that leaf with the atmosphere, which is going to be related to some characteristics of the leaf itself, as well as the wind speed. Wind is a hugely important factor when it comes to water loss.
And leaf level measurements do not generally scale up to canopy level measurements when you're taking stomatal conductance or leaf level transpiration even.
Yep.
Just the canopy resistance to water transport makes a big difference there.
There's not only complexity at the leaf level that needs to be taken into account if you want leaf level transpiration, but canopy architecture can be extremely complex. Right. So scaling those processes can be difficult. So other measurements can be helpful with that. Something like LAI can help to understand canopy architecture or at least biomass, and that can help. But you're right, taking a direct scaling up of a leaf level measurement can be very difficult. So why is it important to have an accurate leaf temperature?
In stomatal conductance
when measuring stomatal conductance, because it's...
well, that kind of depends on your method, right? If you are measuring, if you're using stomatal conductance to measure or to calculate evapotranspiration, leaf level evapotranspiration, then an accurate leaf temperature is critical to calculating the vapor pressure deficit, right? Because that vapor pressure deficit is basically your partial pressure of water vapor in the air minus the saturation vapor pressure of the leaf at that temperature.
Okay.
Or did I get that around? It's one minus the other.
Yeah.
Whichever one turns out to be positive. And so that leaf level temperature is critical for measuring that saturation vapor pressure.
And that I think that kind of speaks to one of the underlying assumptions that we are making in these measurements is that we assume that the inside of a leaf is at 100% relative humidity.
Right.
It is fully, the vapor pressure is at saturation, which means that we are able to simply take the leaf temperature and calculate a concentration of water inside of that. So if your leaf temperature measurement is inaccurate, that pool, which is what we are using in Fick's law, that pool size is going to be inaccurate as well, and throw that off. So it is important to get accurate leaf temperature measurements when you're doing this for that reason. And that assumption, that we use that all across the board in physiological measurements.
It's a pretty common assumption.
Yeah, it's baked into a lot. Okay, so we've talked a lot about some leaf level measurements, talking about stomatal conductance. How can we scale that up? What we mentioned LAI.
Right.
How do we scale up from the leaf level up to the canopy level?
Well, leaf area index is a pretty common proxy for canopy size, right? And that leaf area index is the kind of the layers of leaves that you have. So if you have a area of ground that has, if you have 1 meter of ground area that has exactly 1 meter of leaf area above it, your LAI is 1, right? Say you've got 3 full leaf layers above that 1 meter area of ground, your leaf area index is 3. And so leaf area index is frequently used as kind of a proxy for your canopy mass. And you can use that to You've got certain canopy parameters of assimilation or stomatal conductance or whatever. And if you want to estimate that across a larger area or across a canopy, then LAI is one of those variables that you can use to make that jump.
Okay. So you're saying I need to go out to the forest and start picking up leaves and measuring them, get an estimate of LAI?
Well, that's where you can use something like the LP80. Some remote sensing indexes can give you an estimate of leaf area index. What's called a septometer measures canopy light interception, and that is directly related to the leaf area index.
So there's a couple of different techniques in what you just mentioned there, where you've got some what we would call ground truthing techniques, where you're going out to the forest and measuring it on the ground to see what it does as a point. And then there's also satellite-based products out there too that allow you to take those ground truth measurements and scale them up to ecosystem level,
right,
or global levels. So we can really follow from a leaf level measurement and then scale that process up all the way across the entirety of the globe. So it's pretty exciting, and it really just depends on what scale at which you are wanting to zoom in, what question you're asking.
Exactly.
We talked about some diurnal impacts on stomatal conductance. What sort of cycles do we see in LAI? With stomatal conductance, we see a very strong diurnal pattern. There's a lot of things that go into that. If we are using LAI to scale up leaf level processes to an ecosystem scale, what sort of cycle parameters do we need to look at for that?
Well, your canopy type, deciduous versus conifer, is going to make a big difference in that. Like evergreen trees naturally are going to have a consistent leaf area index all year round. But in deciduous forests or plants, it's going to be more of a seasonal development.
And LAI, even in agricultural species or short canopies, can be extremely interesting and telling, so long as you have a way of consistently measuring those.
And you can use it as a proxy for productivity, basically how much biomass you're putting on, especially if you have plants that are not woody, because woody material generally indicates secondary growth and longer lived plants, and all of the new biomass might not be going towards what we get for LAI there. How does canopy density influence the microclimate beneath it, particularly in terms of temperature and humidity? Less light generally means cooler temperatures.
Yeah, and that can, that the microclimate impacts everything else that exists down there. So if you've got a dense canopy, that's going to impact what other shade tolerant species can grow and what sort of, we haven't talked anything about animals in this to this point, but that's also going to impact what sort of animals are going to exist down there. So that then speaks to being able to not only measure something about canopy architecture, but then how that impacts the microclimate. You need to be measuring that microclimate both above and below the canopy to understand how this impacts your ecosystem overall.
Right.
We started at an individual stoma, and now we're ending up in space, looking down at the world from a satellite. So maybe that's a good place to wrap it up.
Yep.
So,
all right, that's going to wrap it up for us then. Thank you for joining us today. We hope that you enjoyed this discussion. Thank you again for all the questions that have come in. And again, if you have any questions that we did not answer, please contact us via our website, metergroup.com. Finally, subscribe to the Meter Group YouTube channel to accept notifications to see previous episodes of Office Hours and to get notified when future videos are available. Thanks again, stay safe, and have a great day.